I'm going to show an example of analyzing a circuit by circuit reduction, which is something that we've done with batteries and capacitors before. Now we're just going to do something very similar, but this time we're going to have a single battery connected to some network of resistors. And so instead of talking about things like how much charge is going to end up collecting on each capacitor, we're going to say instead how much current will end up passing through each resistor. And then once we find the amount of current, then we could ask other questions such as how much energy is being dissipated at each resistor, what is the voltage across each resistor, and other related questions. So I've taken a figure out of the Halliday, Resnick, and Walker book. This actually goes along with problem number 80. And I have filled in the values for the different resistances. There are actually only two different kinds of resistors in this problem. A single 6-ohm resistor called R1, and then three different 18-ohm resistors labeled R2 in the figure. And we also have a single EMF device, which is just a fancy name usually for a battery, and that's a 12-volt battery. Turns out these particular numbers makes the math almost trivial when you get to the final solution and crunching the numbers. So this particular question asks for how much current is going through the middle resistor known as R2. But what we're going to do is just figure out how much current is going through any of those resistors. So the process of circuit reduction is going to start by taking each of those resistors and deciding whether it's in series or parallel with any other resistors. And this particular drawing can make the question a little bit confusing. So what I'm going to do first is, without doing any reduction at all, I'm going to redraw this in a way that might make it a little bit more obvious. And when we have wires, it doesn't really matter what shape we draw the wires. After all, they're just pieces of metal, so we can make them look any shape at all. So what I'm going to do is reconfigure the metal that connects R1 with all of the other resistors and see if this doesn't look a little bit more familiar. So I'll draw the battery exactly where it is in the circuit. I'm going to draw R1 just the way it is in the circuit. It's my 6-ohm resistor. And then instead of having R2 connect down here where I just circled, I'm just going to move that connection to a different spot on the wire further up here. This is going to muddle my picture a little bit, but now what I have is R2 connected like that, and this connection is also made on that same wire, and so I can draw it like that, and then the last R2 also connects to that. And notice all three of these end up, there's nothing else between those R2 resistors and the positive end of the battery. And so there is an equivalent arrangement, all of these being 18-ohm resistors that we call R2. Now I think if we put it in those terms, it's going to look a little bit more familiar to you. I'll go ahead and just kind of start with it now. So a 12-volt battery. Now I think you can see that the three resistors known as R2 are clearly in parallel with each other. And we know they're in parallel because if you imagine tracing around the circuit from one end of the battery to the other, and we usually go from the positive end to the negative, which is how we describe conventional current. I'll just trace this with a green pen. We will come out of the positive end of the battery. Now we get to a point here where we can split. We can either go through the top resistor, known as R2, and then through R1 and back to the battery, or a different loop might be to go through the second middle resistor, R2. We still have to go through R1 and back to the battery. That's why R1 is not in parallel with any of these. And then the third option is to go through that lower loop, through that R2. But notice every loop takes us through R1. So because those are all equivalent, those R2s, in terms of the circuit, we can say that they are parallel. So I'm going to get rid of those green lines. And now what I can do is do my first step in the circuit reduction And that is to take those three R2 resistors and call them by a different name, treat them as a single resistor. So I still have my R1, which is a 6 ohm resistor. And now I have R, now what would be a good name for this? We're going to call it 222, because those are the resistors from which I am deriving this. And what is the value of those? Well, when we do the calculation for this, because they're in parallel, we add them as inverses. So that means the inverse of R2 plus the inverse of R2 plus the inverse of R2. And of course, some of you are able to see this a little bit more easily. But if you put 18 ohms in for each of those, you're going to get 3/18ths, and then you're going to invert that 18/3, which is exactly 1/3 of the value that each one is individually. So we are now going to treat this as a 6 ohm resistor. So our new looking circuit, now it's not a new circuit, just a new arrangement, is a 12-volt battery hooked up to two 6 ohm resistors. And these two resistors now are in series. We're down to a single loop, so they must be a series arrangement. So we're going to do one more circuit reduction. And we're going to keep our battery where it is. It's a 12-volt battery. I'm going to treat my resistor as a single resistor, and I'll call this R1222. And with resistors in series, much easier to do the calculation. In fact, we wouldn't even need to write this out, but I will just because this is an illustration for you to follow. It's equal to R1 plus R222. You just sum the resistances together. And so this is going to give us a total of 12 ohms of resistance. So we have accomplished the first, I guess, half of the process, the circuit reduction. And now, as with most circuit reduction, we work backwards. If we can figure out how much current is running through this imaginary circuit here, then we can go back up the line and figure out how much current is ultimately going to result in any one of the resistors. So if we imagine current coming out of the battery and back in here, now again, it doesn't really start or end any one place. It's a complete continuous traveling of the current. This value I'll call the total current, or the current through this imaginary resistor, 1222. Now that's also the current that's flowing through the battery itself. Now to calculate the current, we take the total voltage driving that current, divide it by the total resistance being experienced by that current. And again, I said the numbers were almost trivial here. We get 1 amp of current. Now what I can do at this point is actually go up to my original circuit and say I now know how much current is running through my battery, and that same current, notice it does not split until it gets down here, and so all of that current also travels through R1. In fact, I can just continue it on here and show that up until the point where we have a branching, which occurs here or here, we have the same amount of current in that particular branch. Going back down, now I'm going to use my rules for how current splits. And in this case, because going back up to the previous step, I see two resistors in series that were equivalent to my one final resistor. In series, I have no difference in the amount of current through one as the other. Current does not get used up in any way through a resistor. Whatever we have in one series resistor, we must have through all of them. So that means we have the exact same current, 1 amp, through that. Now again, with the numbers being trivial here, I don't necessarily have to show this step, but I am, because sometimes you'll have more awkward numbers. What I can do at this point, I'll just do it in green, is I'm going to figure out how much voltage difference I have across R1, I'll call it V1, and the voltage V222 across there. Now I sort of work backwards. If I know how much current I have flowing through a resistor, and I know how much resistance that current is fighting through, then I can use the same equation in a different order. So I'll call this V1, I1, and R1. Call it a voltage drop across there. This is 1 amp flowing through 6 ohms. So the voltage across R1 is 6 volts. I would have the same calculation. V222 is also 1 amp flowing across 6 ohms. That's the other 6 volts. Something to always check is that when you go around the entire loop, you have to make sure that all the jumps and drops cancel each other out. We have a 12-volt jump as a result of the battery, and now we have 2 6-volt drops across each resistor. Okay, now I can use my other rule for resistors in parallel. Remember, this drop across 222 was really a drop across, and I will draw it up here on this figure, a drop across this side of the network and this side of the network. That means there must be a 6-volt drop across any one of those. So when they're in parallel, we have the same voltage drop, 6 volts across there, or there, or there. I know I'm cluttering my picture a little bit. I'm trying to illustrate this with the use of color as I explain it. So now our final calculation would be, all right, how much current is running through any one of those branches? I'll go back to my system of using red. Now I know I have, in this arrangement here, I already figured out 1 amp of current. What makes this problem kind of nice is that you have identical resistors where it branches off. So when we use the phrase that current wants to go through the path of least resistance, there is no path of least resistance here. They're all equally resistant paths. And so there's no reason why it would want to split unequally. But what we can do here is just go ahead and use the more formal approach and say that the current through R2, let's say we're working for at the top one here, is 6 volts going through 18 ohms. We're going across 18 ohms, which is 0.33 amps of current. And I would do the exact same calculation through any one of these. So the current going through this way is a third of that full amp, and then another third continues on and goes up this way, 0.33. I would do an identical calculation, and then the last 1/3 goes through this lower branch, 0.33 amps. Another fundamental point here, it makes no difference as to the proximity to the battery. One might think that being closer to the battery means you get more than your share of the current. There's no reality to that whatsoever. You know, everything connected by metal means, but really is with resistance-less wires, absolutely no difference between being that bottom R2 and that top R2. So now we've gone above and beyond what the original question was. The original question was, what is the current through this? It is going rightward through this resistor, and that is 1/3 of an amp. Again, you could also turn this into a question, how much, what is the rate at which energy is being dissipated? You know, that's what resistors do. They take one form of energy, in this case electrical energy, and they turn it into a different form, such as heat energy. And the rate at which that happens is known as the power that's being dissipated. So we could do an equation I squared R to calculate that. Again, not a hard number to do here. But I think I'm going to stop there. You've seen the basics of the reduction process, and then as we go in reverse to figure out how much current is running through each branch by using two main rules, that resistors in series have the same amount of current through them and the same amount of current as that combined resistor, such as R1222, and then up above we use the rule for parallel. When you have resistors in parallel, they have to have the same voltage across them. So I'll quit there, and hopefully if you see another circuit like this with a single battery and an arrangement of resistors, you'll be able to use circuit reduction to solve that. Good luck.